Hello. Last time we looked at closed unbounded sets and their enumerating functions, which turned out to be equivalent to a concept called a normal function. So any strictly increasing function from a regular cardinal to a regular cardinal, this is going to be normal if and only if its range is a closed unbounded set. What we're going to show now is that normal functions actually have very many fixed points. In fact, we'll see that they have a closed unbounded collection of fixed points below the regular cardinal, which is their domain. So I'm talking now from the bottom of page 20 now, lemma 213. After that, we will go on to consider stationary sets. Now, stationary sets are also rather thick sets below regular cardinals. Closed unbounded set is, of course, it has the same order type as the regular cardinal itself. That's what the enumerating function shows. And it's closed, the enumerating function is closed at limits. If you enumerate a stationary set, you won't find that the range of that function is closed. In other words, the stationary set itself is not a closed and unbounded set. It's an unbounded set, which actually, it does contain a lot of its closure points, but not necessarily all of them. But it's also a very thick set in that it'll intersect every closed and unbounded set. But first we'll look at the fixed points for the closed unbounded sets. So at the bottom of that page. So we're going to look at lemma 213 and its proof. So the idea here is that I've got a closed unbounded set. So we have a regular cardinal, and I have C contained in omega, where C is CUB. And we have FC is the enumerating function for C. And we're going to look at the collection here of points less than omega, such that the alphath point of C is itself alpha. And this is why it's a fixed point. Then D is itself CUB in omega. And because the range of any normal function is a CUB set, I could rephrase this for normal functions, saying that any normal function has a CUB set of fixed points. Set of fixed points. I'm going to write FP for fixed point here. So this just follows from the above and the fact that a normal function's range is CUB. So let's reason as to why this is shown. So I'll abbreviate by just writing F for FC here. Let's show the fixed points, or D here is unbounded. So pick any gamma less than omega. We'll find an element of D that's bigger than gamma. So this will show that D is unbounded. So we do the following. I'll define an omega sequence of points. I'll start with gamma 0 to be gamma. And f of gamma n, I'll call that gamma n plus 1. And then gamma omega I'll define to be the supremum of the gamma n's. So the picture is kind of straightforward. Here's omega. Here's the gamma that you gave me, which I'm going to call gamma 0. And here's f of gamma 0. And I'm going to call that gamma 1. And here's f of gamma 1. And this I'm going to call gamma 2. I didn't leave myself much space. The supremum of these gamma n's will be called gamma omega. Let me shift these up. So this will be gamma omega. And we just reason that gamma omega is a fixed point above gamma. Indeed, it'll be the least fixed point. So the claim is gamma omega is a fixed point. Because f is this normal function, it's continuous at limit points, it suffices to show that the range of f on gamma omega is contained in gamma omega. So proof of claim. Pick any eta that's less than gamma omega. So let me draw the line out horizontally. Gamma 0 here. Here's gamma omega. If I pick any eta that's less than gamma omega is the supremum of the gamma n's. So what I've got is that eta is less than some gamma n. And for some least n, eta is less than gamma n. Okay, and this is less than gamma omega. So I apply f, which is an order-preserving function. So I'm going to have f of eta is less than f of gamma n, which of course is just what I was calling gamma n plus 1. So it's still less than gamma omega. Hence, eta was just a typical thing less than gamma omega here. So the range of f applied to gamma omega, all of this stuff is contained in gamma omega. That's what these lines mean here. Okay, so everything less than gamma omega gets sent to something less than gamma omega. The function is strictly increasing, so it's 1 to 1. This can only mean that f of gamma omega is the supremum of the previous things. As f is continuous at gamma omega, right? It's a limit ordinal. It's the sup of the gamma n's. So we thus have that f of gamma omega is the supremum of the f of alphas for alpha less than gamma omega here. And by star, let me call this star. And this itself is then just gamma omega by star here. So it's a fixed point. So the claim is proven. So the fixed points are unbounded. And now we just make a remark that they're closed. So I pick any point less than omega with D intersect mu unbounded in mu. So for closure, I need to show that mu is in D. But actually, it's the same argument as we just had for gamma omega up here. By the same argument as for gamma omega above, we'll have that f on mu is contained in mu. Because if you give me an eta that's less than mu, eta is less than one of the fixed points in D. If eta is less than, mu, then eta is less than gamma in some D below mu. This is a fixed point. So f of eta, f being in a strictly increasing function, is less than f of gamma, but this is gamma, it's a fixed point. So I picked something arbitrarily less than mu, and I showed that f of it was less than mu. So this holds. And again, the continuity of f at limit points means that f of mu equals mu. Continuity at limit points says that f of mu equals mu. So mu is in D, it's a fixed point. So D is closed and we've finished the lemma. 213. Okay. So definition 214 is just a piece of notation, but it's important. It will come back to us. I just take any class of ordinals, then the star operation just says is the collection of limit points of things in E. Of limit points E. Namely, E star is the collection of those beta such that E intersect beta is unbounded in beta. So again, note that E star consists just of limit ordinals. although E may have successor ordinals. Okay. So this is beta in ON. So by definition, E star is always closed, right? It's the closure of E, right? It's closed because of how it's defined. So we think of it as the closure of E. So I want to look at exercise 2.7. And this was 2.14. Exercise 2.7 is kind of quite fundamental. So let me go through it, or at least some of it now. So what we've got, the setup is, again, I've got a regular cardinal, and I've got two closed unbounded sets. CUB in omega. And the exercise is to say, show that D intersect C is CUB in omega. So the intuition here is that the set C and D, I said these are kind of thick or rich below the regular cardinal. Well, they're so rich that they intersect each other in also a rich set, a thick set, a closed unbounded set here. So let's see how this goes. And this is a bit similar to finding the fixed points from before. Here's omega. Here's C. And here's D. So again, you give me a gamma, and I'll identify something in D intersect C that's above gamma. This will establish unboundedness. So let gamma be less than omega be given. So it's some arbitrary. Okay, let gamma 0 bigger than gamma here be in C. I know of such a thing in C because C is unbounded. So I'll pick this one here. So this is by unboundedness of C. Now D is unbounded, so there is something in D that's above gamma 0. Okay. Let gamma 0 be less than gamma 1 be in D. Again, now I use by unboundedness of D. Okay, so this is above here. Now all I'm going to do is just zigzag backwards and forwards. I'll pick a gamma 2 that's above gamma 1 in C. Right? Then I'll pick a gamma 3 that's above gamma 2. And I just zigzag backwards and forwards, defining gamma 2n's over here and gamma 2n plus 1's over here. And I'll let gamma omega again be the supremum of all of the smaller gammas. And just as above, gamma omega is going to be a point that's in both C and in D, as it's a limit point of the gamma 2n's and it's a limit point of the gamma 2n plus 1's. So in words, that's what happens next. So zigzagging, pick gamma 2 as gamma 2n plus 1 bigger than gamma 2n in D, and gamma 2n plus 1 less than gamma 2n plus 2 in C. That's my zigzag going on. Right? Let gamma omega be the supremum of the gamma n's. But actually, this is the supremum of gamma 2n's, and this is the supremum of the gamma 2n plus 1s. Let me abbreviate like this. But these guys are all in C, and these are all in D. C is closed, D is closed. So this supremum is in C, and this supremum is in D. So we've done it. We found a gamma omega that's in both C and D. C, and here this is in D. And here we use the closure of C. To get this, and here we use the closure of D. So gamma, our original gamma you gave me is less than this point, and this is in C intersect D. So C intersect D is unbounded. In omega. Okay, we have to justify two things. We want that C intersect D is closed and unbounded. We've just done the unboundedness. We need closure. To show C intersect D closed. Again, this is kind of similar to before. I'm tempted to leave this as an exercise. So just take any mu less than omega with C intersect D intersect mu unbounded. And now it's just logic. C is unbounded in mu, but C is closed, so mu is in C. D intersect mu is unbounded in mu, so mu is in D. Ergo, mu is in both. Are unbounded in mu. Hence, mu is in C and mu is in D. So it's in their intersection. So we finished the exercise, or at least that part one. So what I'll leave here is the rest of the exercise. Consider part two. So let me just think of what you would do for an easy warm-up for part two. So instead of just two sets, let's suppose we have an omega sequence of sets. Each Cn CUB in omega. We can show that the intersection of them all is CUB in omega. We just did it with two sets, C and D. By induction, we could do this for any finite n. But you may be able to see that if we can do it for finite n, we can actually do it for an infinite sequence. And this is the germ of the idea for doing it for longer sequences as well. So imagine what we have here. Here are our sets C0, C1, C2, C3 going out here. This is omega going across the top. And we want to replicate the argument we just did. So we want to show that this is unbounded. So you give me a gamma. Now, so I pick, let's say, gamma 0, 0 in C1. Choose gamma 0, 0 here in C0. Now, by unboundedness of C0, I won't say that each time. Now we pick something bigger in C1. And I'll call this gamma 0, 0. The next one is going to be gamma 0, 1 to be in C1. And this will be here. And in general, we'll have gamma 0 n less than gamma 0 n plus 1 in C n plus 1 as we go across here. So we've got an omega sequence of points increasing this way. So this is the first pass through. So at gamma 0 omega, we'll let that be the supremum of the gamma 0 n's here. So this is something off to the side. Now I have to draw this over here. Now gamma, this is less than omega. Why? That's because omega is a regular cardinal, and this is an omega sequence. So this point has got cofinality omega, little omega. Right? So, but this has got cofinality big omega. Right? So this is true because big omega is regular. So it's over here. And now I repeat the process. I can take this over here. So I zigzag back, and I call this gamma 0 omega. And now I do all of this again. And this I'll call gamma 1 omega. And I repeat this pattern, again, omega many times. Right? And my gamma that I want in this intersection, let's call it gamma omega omega, is going to be the sup of the gamma k omegas. Supremum of the gamma n omegas. So now check. Right? By construction, I've got right, gamma omega omega. This is also the supremum of the let me just make sure I've got my gamma 0 omega here. It's the supremum of these gamma 1, gamma 1. It's also the supremum of the gamma n, or gamma n m's here. So this here is going to be in each of the CNs. Of the CNs here. So this is the germ of how to show that the intersection here of the CNs is unbounded. Hence this here is unbounded. The closure is just the same as for the two elements when we just had C and D. It would be clearer if I just said fixed M, right, for each M. So this equation shows then that this is in Cm here for each M. Because it's in Cm for each M, it's in the intersection of the CMs. Right. Now, the exercise itself says actually something more than this. It says we can have longer sequences of CUB sets. This was just of length omega. It said I can have as many CUB sets as I want, as long as the sequence of them itself has length less than omega. So actually, if I've got, let me try and seek psi, right? I've got this sequence here of closed unbounded sets, and I've only got gamma of them. Where gamma is less than omega. This bit's important, right? So the length of the sequence is less than the cardinal, which they're all CUB in. Right? Then the intersection of psi less than gamma of the seq psi is CUB in omega. So actually what we were doing above was just the case when gamma equals omega. So above we looked at gamma equals omega. So what would we need in this picture to make this work if this dot, dot, dot included seq psi for psi going all the way up to gamma? Well, actually nothing much more. We just need to extend the picture with more vertical lines. Right? And instead of just having, at least on the first row here, gamma 0 ends in the CNs, I'd be saying, let's have gamma 0 xi's in the seek size. I would just make the picture go longer in this direction. So I would just have here omega up at the top, and here's C0, and here's C1. And I'm undaunted by the fact that we've got a very long, here's seek psi, and here will be seek psi plus 1. The fact that this psi is bigger than omega doesn't faze me, right? Because I know I've got less than omega, many of all of these. And I'd start out with my picture in the same way. The first pass through, we the 0th paths, if you like, gamma sub 0 is in C0. Here's something larger in C1. And by the time we're up here, we're in gamma 0 psi. Here, and something larger in gamma 0 psi plus 1. Dot, dot, dot. And now my, I could say gamma 0 gamma. Used the same letter twice. Let me just to, I'm not going to say much more. Let's call this one gamma bar here. So psi plus 1 and gamma 0 bar here. This will be the supremum of the gamma 0's psi for psi less than gamma bar. And the same reasoning would show, right, that here we're less than omega. Okay, I'll let you answer why. And now we repeat this. We take this gamma 0 gamma bar here and now increase things. And we repeat. So I'm going to leave that there and let you puzzle out, at least try the omega case first in detail to check that you understand that. Right? Even if you find this gamma bar case a little daunting. So let's continue. Definition 2.16. The beth function. So this is the second Hebrew alphabet letter. So the aleph function enumerates the cardinals in increasing order. The beth function enumerates the size of the power sets in increasing order. So beth 0 is the same as aleph 0, or omega sub 0. But beth aleph plus 1 is 2 to the beth aleph. So recall this is just the size of the cardinality of this ordinal, the power set. Now, if the continuum hypothesis or the generalized continuum hypothesis held, 2 to the beth alpha is always the next cardinal. So actually, 2 to the beth 0 would just be aleph 1. And then 2 to the beth 1 is just 2 to the aleph 1. Well, that will be the next cardinal. It would just be aleph 2 if the generalized continuum hypothesis held. For limit lambda, this is the supremum of the previous beth numbers. So again, this function, if you like, the beth function, This is a normal function. And its range is contained in cardinals here. So continuity assured by here. The fact that it's increasing is by Cantor's theorem that the size of a power set is always bigger than the size of the set itself. So if the GCH holds, so that is for all alpha, 2 to the aleph alpha is aleph alpha plus 1, then we're going to have for all alpha, aleph alpha is beth alpha. Okay, a little exercise, proof by induction on alpha. But if we don't know the GCH holds, there's no reason why we would have these equations here, right? Beth 1 might be some enormous large cardinal number, right? Just the size of 2 to the aleph 0 could be large, right? Doesn't contradict the axioms of set theory. But GCH is saying everything is nice and minimal to some extent, right? So I mentioned 2,9. So actually the Beth numbers give us the size of the V hierarchy. And because Beth 0 and aleph 0 is the first infinite cardinal, there's a little bit of a wrinkle, right, in this numbering here. Because the VNs, they don't occur in this definition here. The definition starts at omega. Right? So that's why there's this omega that's down here. Okay, so that's a function that'll recur later. I now want to mention, people find this a bit tricky at first. So I'll mention it and leave it for you to think about for a bit, but then I'll do it perhaps next time. Okay? But I'd like to talk about this concept. So this is called diagonal intersections. So again, our setup is as CUB sets. I've got a regular cardinal. And now I've just got a collection of subsets of omega. So there's one thing to note is that I'm not saying it's a short sequence. There can be as many sets here as omega, each size here. So we've got subsets of omega. Yeah. And in the definition, there's nothing about these sets being closed and unbounded. It's just a definition. The diagonal intersection of the sequence here, V size, right? So it's the set D. Yeah, and there's a little diagram to go with this. So sometimes this is written triangle xi less than omega here. So it's not the exact intersection, it's related to the intersection, but it's not the intersection. So the diagonal intersection of the xi sequence is the following. It's the set of points less than omega, so that alpha is in all of the sets, all of the E sets, whose index is less than alpha. So it's like it's alpha's in all the precursor sets. Alpha is not in the intersection of them all. Alpha is just in the ones in the intersection of those that happen to have a smaller index than alpha. So another way of saying that is for all beta less than alpha, alpha is in E beta. Right? So what I was describing was saying it's in the intersection of the beta less than alpha of the E beta. So it's a logically equivalent way of writing that. So this sort of looks like the following. Again, here's omega up at the top. Here are my sets, and now I've got possibly an omega sequence of them. Here's E0, E1, here's some xi, and maybe I've got omega of them, big omega of them. So here's a point alpha. Alpha is going to be in the diagonal intersection if it's in all of the E betas where beta is less than alpha. So it's going to have to be in all of these up to, right? Well, we're enumerating them this way, right? So I can think of omega as being enumerated out here. Maybe here is E alpha. So alpha is going to have to be in all of these previous ones. Right? So if I were to kind of draw a diagonal, here's E alpha up here like this. The things in the diagonal intersection are the things that are in as it were, the colored area. I could color in the upper triangle here. So to be in the diagonal intersection, for alpha to be in the diagonal intersection, it's got to be in all of these E betas here. Well, here's beta less than alpha. So there's two things to show, right? Which are, I think you can be pleased with yourself if you can work these out yourself. But it's a bit tricky, right? Suppose all the xi, right, for xi less than omega are CUB. That wasn't part of the definition of diagonal intersection, but now let's suppose they are. So that D is CUB. Now note that in general, the intersection of capital omega many closed unbounded subsets of capital omega could be empty. If xi for xi less than omega are all CUB in omega, we may have the intersection of the xi, xi less than omega, is empty. Simple example shows that. Set xi to just be the ordinals below a set of tau less than omega, which are bigger than xi. So it's just the end segment here. I could write it as an interval. Right? Things between xi and omega. Each of these is unbounded in omega, obviously, and it's closed because it's everything above xi. In omega, but the intersection is empty because anything less than big omega falls out of one of these xi's. Right. Okay, so the straight intersection of omega many CUV sets can just be plainly empty. But this fancy semi-intersection that goes on in here is preserving the CUV-ness. Right? So if I take the diagonal intersection of these thick sets, I still get a thick set rather than the empty set. So you might like to think about this for next time, but I will go through this again at some point. Okay.